Now the next video is on transmission electron microscopy. This is also called as TEM. Transmission electron microscopy was a technique developed to obtain magnification and hence details of a specimen to a much better level than the conventional optical microscopes. In transmission electron microscope, a beam of electrons is passed through an ultra-thin specimen interacting with a specimen as it passes through. When electrons are accelerated up to a high energy levels and focused on a material, they can scatter or backscatter elastically or inelastically or produce many interactions, source of different signals such as X-rays, Auger electrons or light. Some of the are used in transmission electrons microscopy. An image is formed from the interaction of the electrons transmitted through the specimen. The image is magnified and focused onto an imaging device such as a fluorescent screen on a layer of photographic film or to be detected by sensors such as CCD camera. TEM works like a slide projector. A projector shines a beam of light which transmits through the slides. The pattern painted on the slides only allow certain part of the light beams to pass through. Thus, transmitted beams replicates the patterns on the slides, forming an enlarged image of the slides when falling on the screen. Transmitted electron microscope work on the same way except that they shine on a beam of electrons through the specimen. However, in TEM, the transmission of electron beam is highly dependent on the surface properties of the material being examined. Such properties include density, composition, etc. For example, porous materials will have more electrons to pass through, while dense materials will have less. As a result, the specimen with a non-uniform density can be examined by this technique. Whatever the part is transmitted, the project is projected onto the phosphorus screen for the use to see. Now, the imaging modes. The most common mode of operation for a TEM is the bright field imaging mode. In this mode, the contrast formation is formed directly by the occlusion and absorption of electrons in the sample. Thicker regions of the same and regions with a higher atomic number will appear dark. Worst regions with no samples in the beam path will appear bright, hence the term bright field. This mode is obtained by the intentionally excluding all diffracted beams and only allowing the central beam passing through the specimen. This method is quite useful to study the microstructures of the samples in a plane view and number of multi-layers from cross-sectional view. The plane view images help in understanding the formation of interior microstructure and determining the average size of the particle. Now, the next imaging mode is dark field. This is also formed by magnifying a single beam, but this time one of the diffracted beam is chosen by many of the suitable aperture that blocks the central beam and the other diffracted beams. This method is quite useful to study the orientation of the particles in a particular direction. Now, next one is the diffraction mode. This is obtained intentionally by intentionally excluding a central beam and collecting all the diffracted beams as shown in figure. Now, a thin crystalline specimen is subjected to a parallel beam of light energy electrons as the wavelength of a high energy electrons is few thousands of the nanometer and spacing between atoms in a solid about 100 times larger. The atoms acts as a diffraction grating to the electrons which are diffracted. As a result, the image on the screen of the TEM will be a series of spots or rings. Okay. Now the application part. A transmission electron microscope is ideal for number of different fields such as life sciences, nanotechnology, medical, biological, and material research, forensic analysis, germology, gemology, and metallurgy, as well as industry and education. TEMs provide topographical, morphological, compositional, and crystalline information. TEM can be used in semiconductors analysis and production and the manufacturing of computer and silicon chips technology. Companies use the TEMs to identify the flaws, fractures, and damages to micro-sized objects. Okay. TEMs provide the topological and graphical information also. The images allow researchers to view samples on the molecular level, making it possible to analyze structures and textures. But there are some limitations. TEMs are large and very expensive and laborious samples preparation. Potential artifacts from samples preparation, operation and analysis requires special training. Samples are limited to those that are electron transparent. And TEMs require special housing and maintenance. Images are black and white only. Now the X-ray diffraction. The next one is X-ray diffraction. The XRD effects are observed when the electromagnetic radiation impinges on the periodic structures with a geometrical variation on the length of a scale of wavelength of the radiation. The interatomic distances in the crystal and molecules amount to 0.015, 0.15 to 0.4 nanometer, which corresponds in the electromagnetic spectrum with the wavelength of X-ray having photons energies between 3 to 8 kilo electron volts. There are three different types of interactions in the relevant energy range. In the first, electrons may liberate from the bound electron states in the process of photonization, since energy and momentum are transferred from the incoming radiation to the excited electrons. Photonization falls into the group of inelastic scattering processes. In addition, there is a second kind of inelastic scattering that the incoming X-ray beams may undergo, which is termed Compton scattering. Also, in this process, energy is transferred to an electron, which proceeds, however, without releasing the electron from the atom. Finally, X-ray may be scattered elastically by electrons, which is named Thomson scattering. In this process, the electrons oscillates like a Hertz dipole at the frequency of this incoming beam and becomes a source of dipole radiation. Okay. Now, there are some applications like pharmaceutical industry. X-ray diffraction can be used to unambiguously characterize the decomposition of pharmaceuticals. An XRD pattern is a direct result of the crystal structures which are present in the pharmaceutical under the study. In forensic science also, the XRD is used mainly in contact trace analysis. For example, the contact trace are the points or the paint flakes, hairs, glass fragments, stains of any description, and loose powder material. The identification and comparison of trace quantities of the material can help in the conviction or exoneration of a person suspected of involvement in a crime. The next one is geological applications. The XRD is the key tool in mineral exploration. Mineralogists have been amongst the foremost to develop and promote the new field of X-ray crystallography after its discovery. Thus, The advent of XRD has literally revolutionized the geological science to such a degree that they have become unthinkable without this tool. And this is used in microelectronics industries also, as the microelectronics industry use silicon and gallium arsenide single crystal substrates is integrated circuit production. There is a need to fully characterize these materials using XRD, and there are some limitations. The XRD is having some limitations. Homogeneous and single phase material is the best identification of an unknown. Must have access to a standard reference file. Inorganic compounds requires tenths of a gram of material which must be ground onto the powder. For mixed materials, detection limit is approximately 2% of the sample, and peak overlay may occur and worsen for high angle reflections. Okay. Thank you.